is meter per hour. This is our final answer. So we are done with all the 8 questions of this paper. This was definitely one of the tougher papers. Unlike in 2020 when the paper was very easy, it was comparable to 2019. 2019 had a pretty tough paper too. This was one of the tougher papers, and as you will know, the cutoff for this paper was also very low. So don't worry if you can't solve all of the questions when you sit to solve this. This was a tough paper. Even I could solve just 4 questions in the exam hall. So be pretty satisfied if you are done with about 3 or 4 questions in 2 hours time. Hello again, I am Deepta. I am a first year undergrad at ISI Bangalore, and in this video we are going to have a discussion on the UGB paper of ISI Entrance 2021. This was one of the tougher papers of ISI Entrance and the one that I attempted to get admission into ISI Bangalore. This question paper has a lot of interesting questions too. So without wasting any more time, we'll just start. We'll start with the first question. The first question tells us that there are 3 cities, each of which has n citizens, and every citizen in each city has exactly a total of n plus 1 friends in the other 2 cities. Show that there exist 3 people, one from each city, such that they're friends. That is, there exists a sort of a triangle. We are told to assume that friendship is mutual, which means that, say there are 2 citizens A and B. So if A is a friend of B, it is given that B is also a friend of A. So we'll start with the first question. This is P1. Say these are the 3 cities. City 1, City 2, and City 3. We'll call these as C1, C2, and C3. From all of these 3n citizens, we pick, let A be the citizen. We are calling a specific citizen A. Let A be the citizen with the maximum difference. I'm sorry. A be the citizen with the maximum difference between the number of friends he has from the other 2 cities. I'll clarify what that means. So if this is a citizen, say X, and it has some friends from here, so say it has A friends from C2 and B friends from C3, then by the difference between the number of friends that X has from the 2 cities, I mean this number, modulus of A minus B. So, and we are calling the citizen that has this, for whom this difference is maximum, as A. So A has the maximum difference between the number of friends he has from the other 2 cities. Okay. So, and without loss of generality, we can assume that A belongs to C1. A can belong to any of these 3 cities. We'll just assume that, without loss of generality, A belongs to C1. So say this is A. And suppose A has K friends from C2. Suppose A has K friends from C2 and if it has K friends from C2, then it will have, since it has a total of n plus 1 friends into exactly, then it will have n plus 1 minus k friends from C3, from C3. So this has I will use a highlighter here. Say these are the k friends of A. These are the n plus 1 minus k friends of A from C3. Okay, these are k friends, and these are n plus 1 minus k friends of A from C3. Okay, and we'll just assume that k is greater than this quantity. K is greater than n plus 1 minus k. That is, A has more friends in C2 than it has friends in C3. So we'll assume that instead of saying more, we should say that A has at least as many friends in C2 as it has in C3. So assume that K is greater than equal to n plus 1 minus K. Since we said that A has the maximum difference between the number of friends he has from the other two cities, in mathematical notation, that just means that K minus n plus 1 minus K equals 2K minus n minus 1 is the maximum value of the difference, right? We'll highlight this because we will need this in our solution. So it's okay. So now we look at a specific friend of A from C3. We are picking C3 because C3 has the lesser number of friends than C2. Okay, so say here, say B is a friend of A from C3. So B is a friend of A from C. Okay, we'll just first draw the diagram here. So B is a friend of A from C3, and you will notice quickly that if B is friends with any of these K people from C2, we are done, because we'll just pick that friend, we'll pick A, and we'll pick B, and we will get a triangle, and we are done. So if that is not the case, then B can have at most n minus k friends from here, right? We'll use a highlighter for that too. Here there are n minus k people, so B can be friends with at most n minus k people from C2, right? We will write that down. So assume B is a friend of B belonging to C3 is a friend of A. If B is friends with any of the K people from C2, we are done. So suppose that is not the case, then B has less than equal to n minus K friends from C2. But B must have a total of n plus 1 friends in total. So B must have at least B has at least n plus 1 minus n plus k equal to k plus 1 friends from C3. I'm sorry, from C1, right? So if it is friends with these people here, from this city, from city C1, B needs to have at least, this is at most, so it needs to have at least k plus 1 friends from here. Now we will try to look at the difference, that value of the difference between the number of friends B has from the two cities. Now you will quickly see that for B, that value is, first notice that since we had assumed that k is greater than or equal to n plus 1 minus k, so k plus 1 is easily greater than or equal to n minus k. So for B, the difference between the number of friends he has from the two cities is k plus 1 minus n minus k. And this value is equal to 2k minus n plus 1, right? Now look at this value and look at this value. We had assumed that this value is the maximum, but this value is definitely greater than this. This is 2k minus n plus 1, this is 2k minus n minus 1, and that is the contradiction. So we have arrived at this contradiction from the assumption that B is not friends with any of these people, any of these k friends that A has in C2. So that can't be true. So B must be friends with someone from among these k friends of A, and we will get a triangle then, and we are done with the first question. This is known as the extremal principle, where we assume that something is maximum. We use the maximum value of something. In this case, we are using the maximum difference between the number of friends of each citizen. So we are done with P1. Now we look at P2. P2 is a functional equation question. Here we are given an integer polynomial, and we are given some data about it. We'll write that down in a second. This was actually one of the easier questions. P2, I'm talking about P2. So we are given an integer polynomial, and the data we are given about it is f of 0 is not equal to 0, but f of 1 is equal to 0. Now, by capital A, x comma y, we mean the assertion fxy is equal to fx plus fy minus fx fy. And what do I mean by an assertion? I just mean that whenever I write A, x comma y, I'm substituting the values x and y into this functional equation. Okay, and by bx comma y, I mean this assertion: fx minus y, fx fy equals f of 0. Okay, f of 0, f of x, and f of y, right? So these are the two functional equations that we have been given here. These are true for all integers x and y. And the first part of the question asks us to determine the range set of the function. That is the set. Okay, we are calling this as R. We define as R the set of all integer f of a for all integers a, right? Okay, so as is the case with all questions on almost every question on functional equations, we should first start by putting some random values. Not just some random values, we'll put some good values, like putting x equal to 0, y equal to 0, x equal to 1, y equal to 0. Just putting y equal to 0, putting both x and y equal to 0. These are the common strategies that you apply when you have a question on functional equations. We are going to do the same only. So the first thing that we do is we look at the assertion a 0 comma 0. That is, we are substituting x equal to 0, y equal to 0 into the first functional equation, and that gives us, if we put both x and y equal to 0, we should get f of 0 equal to f of 0 plus f of 0 minus f of 0 squared. So first assertion becomes f of 0 is equal to f of 0 . So rearranging this gives us f of 0 squared is equal to f of 0. This just implies that f of 0 is either 0 or f of 0 is equal to 1. But remember that we have been told that f of 0 is not equal to 0. So f of 0 is equal to 1. This is the data that we will need. So f of 0 is equal to 1. Right. Now we look at the assertion b x comma 0. Now we just put y equal to 0 into the second functional equation. That will give us f of x. We are putting y equal to 0, so that will give us f of x times f of x times f of 0 equals f of 0 times f of x f of 0. So we'll write that down. Give us f of x f of x f of 0 is equal to f of x f of 0, right? Is that right? And then, okay, we already have f of 0 is equal to 1, right? We will use that value. So I'm sorry. Yeah, here we are putting we have 0, so this f of 0 is already becoming 1. This just becomes f of x squared is equal to f of x. Now remember, this is true for all integers x. So for all integers x, f of x is either equal to 0 or it is equal to 1, right? So the range set can be is a subset of the set 0 comma 1. The range set is a subset of the set 0 comma 1, but we have already seen that f of 0 is equal to 1, and we have been given that f of 1 is equal to 0. So the range set is exactly equal to 0 comma 1. So this is our R. That is the set f of a for all integers a. So the function f takes only these values 0 and 1. That was quite easy. Now we move to the second part of the question. Assuming that there is a non-zero integer a such that f of a is not equal to 0, we have to prove that the set b, that is the set of all integers for which f assumes a non-zero value, is infinite. This is the second part. We are assuming that there is a non-zero integer a. Okay, so a is the non-zero integer for which f of a is not equal to 0. But we have seen that the range set is just this. This is just the range set, 0 or 1. So f of a can be either 0 or 1. F of a is not equal to 0. So f of a is just 1. Okay. Now we will look at the assertion a x comma a. This gives us f of x a is equal to f of x plus f of a minus f of x f of a, right? This will give us, see, this f of a, this value is equal to 1, this value is equal to 1, this right hand side is f of x plus 1 minus f of x. So f of x a is equal to just 1, right? and this is true for all integers x. So whenever you put a non-zero integer x here, you will get f of x a is equal to 1. So if you consider this integer only, I will use a highlighter. If you consider this integer, you will get an infinite set for which the value of the function is non-zero, and being non-zero we just mean 1. So in general, you can just look at the set of values f of a to the power k. This is equal to 1, where we are putting x equal to a to the power k minus 1 for natural numbers k. Right. So in this case, we for whatever natural number k you put, f of a to the power k is equal to 1. This proves that the set of integers for which the value of the function is non-zero is infinite. So as you see, this question is done. This was a rather easy question. Now we have a more involved question. Question 3. For question 3, we are asked to prove that every positive rational number can be expressed uniquely as a finite sum. These are the keywords that we have to prove. Can be expressed, this is one word. I'm sorry. So this is one word that is key, expressed uniquely and as a finite sum of the form of this form. We are in integers and we are given some constraints. So why did I highlight those points? That just means that there are 3 parts to the solution of this question. We first have to prove that every positive rational number has an expression. Then you have to prove that this expression is unique, and you also have to prove that the expression that you get for every positive rational number, it has to be finite. It can't be an infinite sum. It is never an infinite sum. So these are the 3 parts of the solution, and you have to prove each of these 3 parts. This is a more involved question and one of the tougher questions in this paper. Okay. First we are going to prove the uniqueness. Generally, people prove the existence part first, then go to uniqueness. But we are going to prove the uniqueness first because it is going to give us sort of a motivation for the existence part. We'll just assume that such a representation exists, and then we move to prove that this expression is unique, right? Okay, so in order to prove that the expression is unique, we just have to show that each of these coefficients, a1, a2, a3, all the way till an, each of this is uniquely determined. I mean, there can't be a second choice to any of these. So consider a positive rational number. Consider a positive rational number, and say we have this expression a1 plus a2 by 2 factorial plus a3 by 3 factorial all the way till an by n factorial for some natural number n, and we are given that the integer, that ak's are all integers, and the ak's satisfy this constraint for all k greater than 1, right? These are the constants that we have been given. We have to we first prove that this expression is unique. For that, okay, first note, look at this part of the expression. Okay, this this part is just the summation I equals 2 to n ai over I factorial. Each of these ai's are less than equal to k minus 1 or I minus 1. So this is less than equal to the summation I equals to n I minus 1 over I factorial. As you will see, this summation breaks down very nicely into a telescoping series. This just becomes 1 by I minus 1 factorial minus 1 by I factorial. And this is a telescoping series. And the final answer that we get is 1 minus 1 by n factorial. And as you can see, this is strictly less than 1. This is strictly less than 1. So a1 is uniquely determined as just the box or just the integer part of x, right? This is just the integer part of x. The rest part is the fractional part. Okay, so a1 is uniquely determined. Now we move on to the next part. That tells us okay, so we already have x equals a1 plus a2 by 2 factorial plus all the way till an by n factorial. Rearranging this a little bit gives us x minus a1 times 2 factorial. This is equal to a2 plus 2 factorial times a3 by 3 factorial all the way till an by n factorial, right? Again, as you have already guessed, we are going to look at this summation. It's going the process is going to be the same as in the previous step, and later we will just generalize it. We will proceed by induction. This summation is summation as I goes from 3 to n ai by I factorial. This is less than equal to the summation I equals 3 to n I minus 1 by I factorial, and which gives us the telescoping series 1 by I minus 1 factorial minus 1 by I factorial. This is 1 by 2 factorial minus 1 by n factorial. Okay, so multiplying that with 2 factorial times this summation is less than equal to 2 factorial times 1 by 2 factorial minus 1 by n factorial, which is equal to 1 minus 2 factorial by n factorial. And since n is greater than equal to 3, this is strictly less than 1. So again, this entire part is less than 1. Once again, a2 is determined as a2 is the box of 2 factorial x minus a1. This is how we determine a2. So proceeding by induction, proceeding inductively, we get we look at the kth step. Okay, we look at x minus a1 minus a2 by 2 factorial a k minus 1 by k minus 1 factorial multiplied by k factorial. This is equal to ak. So in this kth step, we are just showing how we are determining the kth coefficient ak. Okay, so once again we'll just look at this summation and we'll easily see that this is less than 1. Let's do that. I will skip some steps here because we have already shown this step a couple of times already. This is just 1 by k factorial minus 1 by n factorial. You will get the same telescoping series, and this is equal to 1 minus k factorial by n factorial. Since n is greater than equal to n is greater than equal to k plus 1, this is strictly less than 1. Once again, this is strictly less than 1, so ak has to be the integer part here. So ak is uniquely determined as the integer part of k factorial times x minus summation I equals 1 to k minus 1 ai by I factorial, right? This is the sum. Okay, so this is how we are determining ak, and by induction each of the coefficients, as you can see, is uniquely determined. So the uniqueness part is done. We are done with the uniqueness part. So what we have shown till now is that if such a representation exists, it must be unique. It must be unique. So if such a representation exists, it must be unique. Now we will show that such a representation exists indeed, and you will see why we proved the uniqueness part before. Okay, now we will prove existence. Now we will prove the existence. To prove the existence, we have to show that those coefficients a1, a2, a3, these coefficients exist. So we will define these coefficients as define a1 as just box of x, define a2 as the box of 2 factorial x minus a1, because we have already defined a1. We will use it to get a recursive definition for a2. We get a3 as the box of 3 factorial times x minus a1 minus a2 by 2 factorial, and in general we define ak as the box of k factorial times x minus the summation I equals 1 to k minus 1 ai by I factorial. So this is how we are defining each of the coefficients, and we just have to show, we have already seen that these coefficients work in the previous in the uniqueness part. We have to show that these coefficients they satisfy the constraints ai. We need to show that each of these coefficients is greater than equal to 0 and less than equal to k minus 1 or k greater than 1. We have to show that this constraint holds. That is quite easy. We will use the property of the box function, which says box x is less than equal to x and strictly greater than x minus 1 for all real numbers x. This is the property of the box function that we will use. Okay, so we have ak equal to k factorial x minus a1 minus a2 by 2 factorial minus all the way till a k minus 1 by k minus 1 factorial. Okay, this is less than equal to, we'll just remove the box, x minus a1 minus all the way till a k minus 1 by k minus 1 factorial. This gives us x minus a1 minus till a k minus 1 by k minus 1 factorial. This sum is greater than equal to a k by k factorial. We are using this and this part. We'll bring k factorial to the other side. It's just some simple manipulation. This gives us that a x minus a1 minus all the way till a k by k factorial. We are bringing this term to the left hand side. This is greater than equal to 0. In other words, writing this compactly, ai by I factorial as I goes from 1 to k, this is always greater than equal to 0. So this is a property that we will need. And the other side, ak equals k factorial x minus a1 minus a k minus 1 by k minus 1 factorial. This box is strictly greater than minus 1. This is the other side of the inequality that we will need. This tells us that x minus a1 minus a k minus 1 by k minus 1 factorial, this is strictly less than a k plus 1 by k factorial. And bringing a k by k factorial to the left hand side tells us that this summation I goes from 1 to k. ai by I factorial is strictly less than 1 by k factorial. This is the other side of the inequality that we will need. Okay. These two inequalities, we'll rewrite these two inequalities for convenience. For k positive, k greater than 1, x minus this summation I goes from 1 to k of ai by I factorial. Okay, for convenience, we'll take it till k minus 1. This is less than equal to or strictly less than 1 by k minus 1 factorial and greater than equal to 0. Multiplying both sides with k factorial, we get this is less than equal to k factorial times x minus the summation as I goes from 1 to k minus 1 ai by I factorial. This is k factorial by k minus 1 factorial equals k. So, and you will recognize that the box of this quantity is equal to ak. So ak equal to the box of k factorial x minus I equals 1 to k minus 1 ai by I factorial. This is less than equal to k minus 1 and greater than equal to 0. And we are done. So what we have shown till now is that if such a representation exists, it must be unique. Now we have shown that such a representation does exist. So because we have uniquely determined each of the values a1, a2, a3, and we have also shown that they do indeed exist. Now you will notice that we haven't shown that this summation representation of the rational number x is finite. We haven't shown that this summation terminates. It could be that it goes on till infinity. So but the question requires us to show that there exists a finite sum, and we will do just that. We need to show that the representation is finite. The representation is finite. This is what we will do now. Suppose not. So assume to the contrary. That the sum is not finite. We will look at a representation. Okay, so suppose this is a representation that we have a1 plus a2 by 2 factorial an by n factorial. It is going on. It won't stop. This is an infinite representation. Suppose this is the representation of x that we get, and we want to show that in order to prove our point, we have to show that there exists some natural number n, say n, or any natural number n, after which all of these coefficients here ak are equal to 0. That is, these coefficients just don't exist. They are all 0. They don't exist, and that will prove that this sum is finite, and we will try to do that. So in order to do that, we will remove all of the 0 terms here. So which means that instead of the constant ak less than equal to k minus 1 greater than equal to 0, this was the constant that the question gave us. We will instead look at the constant this is greater than equal to 1. That is, we want all of these coefficients to be non-negative. We want all of these coefficients to be positive. In order to do that, we have to look at a subsequence of the natural numbers. We won't look at a1, a2, a3, a4. Instead, we will look at a I1, a I2, a I3, all the way till a IL, so on. We look at a subsequence, and this subsequence is it consists of only the non-zero coefficients. So suppose x is equal to this summation a I sub l factorial, as l goes from 1 to infinity. Suppose this is the infinite summation that we have, and the property that this has is AIL is less than equal to IL minus 1 and greater than equal to 1. So all of these terms are positive. That is, they do exist. They don't vanish. X is a rational number, right? So X has a representation like this, P by Q, where P and Q, the usual constant conditions, P and Q are both integers, Q is not equal to 0, and P and Q are coprime. So X is equal to P by Q. Now let n be the natural number such that I sub n is strictly greater than Q. That is strictly greater than this denominator. You will see why we need that. It is strictly greater than Q, and for this, now we will look at the following quantity. you will see why we need this in greater than q. Look at the following quantity. At I'm sorry, in factorial p by q minus summation as I'm sorry, we no longer have I, we have L now. So L goes from 1 to n a I L over I L factorial. We're looking at this quantity. You will notice that this is just equal to once again we don't have I, we have L now. Since we are subtracting all of the terms from 1 to n, we will have n plus 1 to infinity. This is equal to a I sub L by I L factorial less than equal to, well, we will use that constant I'm sorry, what did I write? Right, and this is strictly less than this infinite sum, and this, as you see, is just the telescoping series, which is equal to 1. This series converges to 1. So what we have is in factorial times p by q minus this summation L equals 1 to n. This summation is strictly less than 1, but we had this condition in is greater than q. In is greater than q, so in factorial, okay, we look at this quantity. This quantity is just I sub n factorial times p by q minus summation as L goes from 1 to n a I L times in factorial in factorial over I L factorial. So since in is greater than q, this term is a positive integer. Since in is greater than and in, okay, since L is less than equal to n, this term is also a positive integer. So this whole term, this LHS, is a positive integer. This LHS is a positive integer which is less than 1, but there do not exist any positive integers less than 1, and that is a contradiction. So the sum can't be can't be infinite. Therefore the representation must be a finite sum. So the representation must be a finite sum, and we are done. Okay, this was a very involved question, a very lengthy one. Now that we are done with this, we will move to the next one. Okay, we will do the fourth question now. Okay. The fourth question gives us a function which is defined on the positive reals and gives us only positive real values g, and we are given that g is a differentiable function, and we are also given that its derivative is continuous, and we are also given that g of x is equal to x for all positive integers, for all positive real numbers x. We are also told that g is not the identity function, so we have to prove that g must be strictly decreasing. We will start with this. Okay, this is p4. This is okay. This is p4. We have g of x is equal to x. This is actually a very common question, and if I'm not wrong, this is a repeated question of ISI. Probably, I'm not 100% sure, but this a very similar question was asked by ISI in its subjective paper in a few years back. So it has a very standard technique, which you will see. We are given that g of x is equal to x for all positive reals x. G is differentiable, so we differentiate both sides of this equation to get g dash of g of x times g dash x is equal to 1. Okay. Now notice that if at any value of x, g dash x is equal to 0, this equation will give us 0 is equal to 1. That is, if g dash x is equal to 0 at any positive real number x, then we will get then we will get 0 equal to 1, which is just absurd. So you have so g dash x is never equal to 0 for all positive reals. So g dash x, it can either be greater than 0 or it can be less than 0. Now we have been given another data in the question that the derivative is also continuous. And a very important property of continuous functions is the intermediate value theorem. The intermediate value theorem. So now, okay, since g dash x is not equal to 0, it can either be, okay, we will not write that, we'll write it in a different way. If there exist two positive real numbers a and b such that the value of g at these 2 points, the value of g dash at these 2 points is different. Say, what I mean by this is, suppose g dash a is positive and g dash b is negative, or g dash a is negative and g dash b is positive, or which we can write it as, if this is less than 0, then by the intermediate value theorem, there exists a real number c in the interval a comma b such that g dash c is equal to 0. Again, as we have already seen, this is not possible. This is not possible. If by the intermediate value theorem, if the value of g dash is positive here, negative here, somewhere it will be 0. That is not allowed. So we conclude that either we have only the following two options: either g dash x is strictly greater than 0 for all x, or g dash x is strictly less than 0 for all x. And as we know, this condition means that g is strictly increasing, and this condition will mean that g is strictly decreasing. And the question asks us to prove that this is actually the correct condition, but we will see why. We will show why this condition can't be possible. Assume that g dash x is positive for all positive reals x. Now, you will also remember that we have the condition that g is not the identity function. Since g is not the identity function, there exists some positive real number k such that either g of k is greater than k. This is not equal to k because g is not the identity function. So since g of k is not equal to k, g of k is either greater than k or less than k. If g of k is greater than k, then since g dash x is strictly greater than 0, g is strictly increasing, we get g of k is greater than g of k. We are just composing g one time. Now this value g of k, this is just equal to k, so this gives us k greater than g of k. And this gives us that k equal to g of k, it is strictly greater than g of k, and we have assumed that this is strictly greater than k greater than k, which is not possible. This is just absurd. So g of k can't be greater than k. On the other hand, if g of k is strictly less than k, again k equal to g of k, this is less than g of k since it is strictly increasing, and this is again less than k. This gives us k is less than k. Again, a very absurd condition. So we conclude that g dash x can't be strictly greater than 0 for all x. So the only condition that we are left with is that, so it must be that g dash x is strictly less than 0 for all positive reals. In other words, g is strictly decreasing. This was a very short and quick solution. And this inequality, this work with the inequality that we have done, it is a very standard manipulation and you should note it. Okay, we are done with the fourth question as well. And we will move on to the next one. We will move on to the fifth question, which is a polynomial question and a limit question together. Okay. This is the fifth question. We are given a polynomial, a monic polynomial. We are given that p of x is equal to p of minus x for all real numbers x, and p of x is equal to x squared for x equal to 0, 1, 2 all the way till 9. We have to find the limit x tends to 0 as of p of x by sine squared x. Okay. Do we have a lot of place here? I don't think so, but it should be enough. So this is p5. We have the polynomial p of x equal to x to the power 20 plus a19 x to the power 19 plus a18 x to the power 18, so on and so forth till a1x plus a0, where the ai's are real numbers. Okay, we are given that p of x is equal to p of minus x for all real numbers x, for all real numbers x. So substituting this into the polynomial value gives us x to the power 20 plus, sorry, x to the power 18 plus a1x plus a0. This is equal to x to the power 20 minus a19 x to the power 19 plus a18 x to the power 18 minus all the way till this plus a0. Okay, since this polynomial equation is true for all real numbers x, we get that all of the odd coefficients are 0. Just compare the coefficients and write. This is what we get. All of the odd coefficients are 0. K equal to 1, 2, 3 all the way till 10. So this A19, A17, A1, they are all 0. So the polynomial, these are all equal to 0, and you will also notice that P of K is equal to 0, K squared for K equals 0, 1, 2. So P of 0 is also equal to 0. Putting that into the polynomial gives us A0 equal to 0. So using these two data, we can write the polynomial more simply as P of x is just x to the power 20 plus A18 x to the power 18 plus A16 x to the power 16, like this till A2 x squared. Okay. Now we will use a second data that we have been given, that is P of k. P of k is equal to k squared for all k equal to 1, okay, k equal to 0 to 9. 0, 1 all the way till 9, equal to 0 to 9. This tells us that the polynomial is of the form P of x equals x, x minus 1, x minus 9 plus x squared. That is, P of x minus x squared has all of these roots. Okay, I'm sorry, I have written something wrong. Since P of x is a 20 degree polynomial, there is another polynomial here of degree 10 plus x squared. So this is our polynomial. Again, P of minus x is this. Now these two values are again equal for all real numbers x. That is x. We can simplify this polynomial once. It will be easier. Since there are 10 terms here, there are 10 minus signs. It all cancels out. So we have P of x equal to P of minus x for all real numbers x. This gives us x times x minus 1 till x minus 9 times P of x is equal to x times x plus 1. I'm sorry, till x plus 9 P of minus x. This is right. Okay. Now, one by one, we can substitute the values x equal to 0. No. The values x equal to 1, 2, all the way till 9. If you put x equal to, not these values, I'm sorry, x equal to minus 1, minus 2, all the way till minus 9. We put x equal to minus 1, the right hand side is equal to 0, the left hand side is non-zero, so q of minus 1 is equal to 0. Similarly, q of minus 2 is equal to 0. In general, q of x is the polynomial x plus 1, x plus 2 till x plus 9. But this is a 9 degree polynomial. Q is a 10 degree polynomial. So there is another term here, x plus s. Okay. Putting this expression for q into this above equation gives us x, x minus 1, all the way till x minus 9, x plus 1 till x plus 9, x plus s. This is equal to x plus 1 all the way till x plus 9 and q of minus x is x minus 1, x minus 2, x minus s, since there are 10 terms here. Okay, comparing the coefficients, we very easily get that s is equal to 0. So q of x is just x times x plus 1, x plus 2, x plus 3 all the way till x plus 9, and the polynomial p of x, is x squared x minus 1, x minus 2 all the way till x minus 9, again x plus 1 all the way till x plus 9. There are 10 terms here and plus x squared. So this is the polynomial p of x, right? We can write this in a more compact form. It will be easy to express. X squared minus 1, x squared minus 4, x squared minus 9 squared plus x squared. Okay, now we evaluate the limit. The main point of the question is to evaluate the limit as x tends to 0 of p of x over sine squared x. This is the limit x tends to 0, x squared minus 1 all the way till x squared minus 9 squared plus x squared. So very easily we can see what we have to do. We just bring the x squared down. Since x is non-zero, we can do that. Squared minus 1 and we will use the very well-known limit that this goes to 1 as x tends to 0. Since this goes to 1, this is equal to, okay, I wrote something wrong here. It would be the equal to sign. Why should it be the implied sign? This goes to 1 and we can then directly substitute x equal to 0 here. This gives the value of this is minus 1, minus 4, minus 9 till minus 9 squared plus 1, and this value is very easily 1 minus 9 factorial squared, and this is our answer. Here's a final answer. So this was a very simple question too, doable question. Okay, we're done with 5 questions and 3 remain. Next, we have a geometry question, which the statement of the question might be a little unclear, but actually the solution is very small, maybe the smallest solution in this whole paper. Okay. Okay. We have come to the end of the page here. We'll move to here. We have written a lot. noticeable. Hmm. So this is P6. For P6, we are we have a equilateral triangle or side length A, and we have said that it lies in the union of 5 equilateral triangles of side length B. We have to show that there exist 4 equilateral triangles of side length B whose union contains the triangle. We all know of the very familiar configuration, the set of points. Okay, we'll come to that later. Little notation: when I say K equilateral triangle, whenever I say K equilateral triangle, I will mean an equilateral triangle of side length, an equilateral triangle of side length K. Okay, so we are given an A equilateral triangle, and we are said that this A equilateral triangle lies in the union of 5 B equilateral triangles. We have to find we need to show a condition on B. Okay, now first we look at the very common configuration, an equilateral triangle. This diagram is good enough. We look at the set of 6 points, the set of the 3 vertices and the 3 midpoints of the sides. This is an A equilateral triangle, not the price. This is an A equilateral triangle. Okay, so if A by 2 is greater than B, this is the first condition that we are exploring. If A by 2 is greater than B, look at this. These lengths are all A by 2. This is A by 2, this is A by 2, this is A by 2, this is A by 2. This 3 lengths are also A by 2. This length is greater than A by 2. This length is greater than A by 2. This is also greater than A by 2. In general, for all of these 6 points, from among these 6 points, whenever we take a pair of points, they are at a distance of at least A by 2. And there are 6 points. So clearly, we cannot cover this triangle with this A equilateral triangle with 5 triangles, with 5 B equilateral triangles if B is less than this side length, this A by 2. So if A by 2 is greater than B, we cannot cover the A equilateral triangle with 5 B equilateral triangles. We will need at least 6. I will check one thing. This is recording. Okay, sorry, excuse me. We will need at least 6 B equilateral triangles. So A by 2 greater than B is not possible. The second possibility is if A by 2 is equal to B. What if A by 2 is equal to B? Then very easily we see the first configuration that comes to our mind is, I'm sorry, These are the 6 points. So if B is equal to the side length, we just take these equilateral triangles. This is one equilateral triangle, B equilateral triangle. So this is another B equilateral triangle. This is the third B equilateral triangle, and this is the fourth B equilateral triangle. This is one, this is one, this is one, and this is the fourth one. So if A by 2 is equal to B, we can cover the A equilateral triangle with 4 B equilateral triangles, which is what the question asks. There exist 4 equilateral triangles of side length B whose union contains triangle, the delta. Now, if A by 2 is strictly less than B, that is, if this B is greater than the side length A by 2, then it's even easier. You can take bigger equilateral triangles like this. There will be a bigger triangle here, bigger triangle here, a bigger triangle here. So you will cover, you will in normal words, you will just cover more than the equilateral triangle, but that still works. We are asked to show that the A equilateral triangle will lie in the union of the 4 B equilateral triangles. So this condition is also done, and the question is over. This is the solution. So A by 2 greater than B is not possible. The only possibilities are this, and in each of these cases we have shown a configuration that works, and that is fine. So the 6th question is also done. We will move on to the 7th question now. P7. In the 7th question, we are given 3 real numbers A, B, and C, which are the roots of a cubic polynomial. And 3 real numbers satisfy A plus B plus C is equal to 6, and AB plus BC plus CA is equal to 9. These values always remind us of the Vieta's formulae, and we will kind of use that, not in general. Okay. We are given that A is strictly less than B is strictly less than C. We have to show this inequality. We will write this down. We'll write this inequality down for easy reference. Okay. To show less than 1 less than B, right? This is what we want. Yeah. Okay. This is what we want to show. Now let P of X be one of the polynomials which has A, B, be one of the cubic polynomials that has A, B, and C as the roots. We'll just consider the monic polynomial for ease, for making it easy. Let it be this cubic polynomial. Or in other words, if you expand this, this is just x cube minus the sum of roots is 6, and the sum of product of roots taken 2 at a time is 9. So this is minus 6x squared plus 9x minus ABC. Okay, so this is the polynomial P of X. The derivative of P of X is 3x squared minus 12x plus 9. This is 3 times x minus 1 times x minus 3. So P can have local extrema at these 2 points, 1 and 3. And we also look at P double dashed x. We won't need P double dashed x, but okay, just as a safety, this is just 6x minus 2. We won't need P double dash x. Okay, we will use P dash x. Since P dash x is 3 times x minus 1 times x minus 3, it is very easy to see that this gives us that P dash x is greater than or equal to 0 in the intervals minus infinity to 1 I'm sorry, union 3 comma infinity. So p dash x is greater than equal to 0 in this portion of the real line, and p dash x is less than equal to 0 in 1 comma 3. This just means, since p dash x is greater than equal to 0, this just means that p is increasing, or we should say p is strictly increasing in minus infinity comma 1. Here I'm keeping 1 open, I'm not including 1, and I won't include 3 as well. And this means the second line, that p dash x is less than equal to 0, p is strictly decreasing in this open interval. Again, I will not include the points 1 and 3, because strictly increasing, strictly decreasing are more comfortable conditions. Since this is not possible, okay, so these are the 3 portions. This is 1, this is 3. The polynomial p is strictly increasing here, strictly increasing here, and strictly decreasing here. Okay. Moreover, we look at the value of p double dash x at these 2 points, 1 and 3. So p double dash of 1 is equal to 6 times 1 minus 2, which is negative. So x equal to 1 is a point of local maxima, a local maxima, and p double dash of 3 is 6 times 3 minus 2, which is positive. So x equal to 3 is a point of local minima. Okay, now p is a cubic polynomial, so it has the 3 roots. And the 3 roots are a, b, and c. 3 distinct roots: a less than b less than c. And the polynomial p can have at most 1 root in this interval, at most 1 root in this interval, and at most 1 root in this interval. Here I mean infinity and plus minus infinity. This is because the polynomial is strictly increasing, strictly decreasing, and strictly increasing respectively in these 3 intervals. Since p must have 3 distinct real roots, we must have a less than 1 less than b less than 3 less than c. That is, this should be a, this must be b, this has to be c. Okay. And for that, the points of local maxima and local minima, these have to be the points of local maxima and local minima, and this has to be positive and this has to be negative, right? We will need those. We'll need this and this. So this is the progress that we have made till now. We have a less than 1 less than b less than 3 less than c. We have to show that this a is greater than 0 and c is less than 4. Okay, now we look at the value p of 1. What is p of 1? This is the polynomial, so p of 1 gives us 1 minus 6 plus 9 minus abc. That is 1 minus 6 plus 9 minus abc. Okay, instead of this, yeah, this is okay. This is equal to 9 plus 1, 10. 10 minus 6 is 4 minus abc. This is strictly greater than 0. Do we need this? No, I don't think so. Okay, let it be. We'll look at another value, that is P of 3. P of 3 is, what is P of 3? 3 cube is 27, 3 nines are 27, 54, 54 minus 3 is 9, 6 is 54. So P of 3 is just minus ABC, and P of 3 is negative. Yeah, this is not where we will use it. So P of 3 is just ABC, and this is strictly less than 0. This implies ABC is strictly greater than 0, but we already know that B is strictly greater than 1, C is greater than 3, so B and C are positive. That gives us A is greater than 0. A little more progress. A is greater than 0. Now we are left to show that C is less than 4. For C less than 4, let's just look at the value of P at 4. Let's see what happens. So P equals, putting x equal to 4 into the polynomial P gives us 76 minus ABC. Okay, now we will use the value of P of 1. ABC is less than, minus ABC is greater than minus 4. Is that true? ABC is less than 4, right? The value of P of 1, since P of 1 is positive, ABC is less than 4. So this gives, this is, since ABC is less than 4, minus ABC is greater than minus 4. So this value is greater than 76 minus of minus 4, which is just 80 and greater, strictly greater than 0. Yeah, 80 and strictly greater than 0. So 4 must be here somewhere, because if C is to the right of 4 and the polynomial P is strictly increasing in this interval, so if the value of P at 4 is positive, the value of P at points to the right of 4 will be even greater positive values. We don't need that. We need the value of P at C to be 0. So C has to be less than 4. C is less than 4, and we are done. So we are done for the 7th question as well. Now we move on to the last question. Finally, we move on to P8. This is another, is a mostly a calculus question. We are given a pond as an inverted truncated pyramid with a square base. This pond is at ISI. The depth of the pond is 6 meters, and the square at the bottom has side length 2 meters. The top square has side length 8. Water is filled in at a rate of 19 by 3 cubic meters per hour. At what rate is the water level rising? Exactly 1 hour after the water started to fill the pond. Okay, exactly 1 hour after the water started to fill the pond, since the rate of filling is 19 by 3 cubic meters per hour, after 1 hour, the volume of water in the pond will be 19 by 3 cubic meters. We'll use that. Okay. We move on to the last question. Yes. Okay. A good diagram is very necessary for this. I think this is pretty good. This is the best I can do. So we put on the values. We will label some points here. We label this as B, this as C, D, E. Let's call this as P, Q, R, and S. Now we just extend these points to meet at a point A. We call this point A, the apex of this whole pyramid. Okay, the apex of the whole pyramid. The side length here is 2 and the side length here is 8. Side length here is 8. Okay, these are all square bases. The bases are parallel. These are all given. So we will write down the data that we already have. After 1 hour, the volume of water is 19 by 3 meter cube. Okay, let the height of this pyramid A, B, C, D, E, this top pyramid, be H. Suppose this height is H. Height of the pyramid A, B, C, D, E, B, H. If this is a H, by similarity, okay, we already have this height as 6. We already have this height as 6. Okay, so by similarity, H over H plus 6, H over H plus 6 is equal to 2 over 8. This gives us H is equal to 2. Okay, we have this height. This is H equal to 2. So you can very easily see that this is kind of like a equilateral pyramid. This is H equal to 2. I don't know if equilateral pyramid is the right word for it, but for the pyramid with base 2 has height 2. The pyramid with base 8 has height 6 plus 2, 8. In general, by similarity, you can prove that the pyramid of height S. So if there is a pyramid here of height S, if this is a pyramid of height S, then the side length of this will also be S. The side length of the square base of this pyramid of height S will also be S. Okay, we'll use this pyramid now. Let's label these points as X, Y, Z, and W. Okay, we consider this pyramid now: A, X, Y, Z, W. A, X, Y, Z, W. The side length is S and the height is S. We already know that. We define by Vs. Vs is defined as the volume of this pyramid. Oh no, Vs is defined as the volume of the portion of the pond. I'm sorry. Volume of the portion of the pond between the two bases B, C, D, E and X, Y, Z. So Vs is just this volume. Vs is this volume that we are looking at. This is Vs. And this is very easy to calculate. This is just the integral from 2 to s of x squared dx, because all of these bases have area x and you are integrating from 2 to s. This is just x cubed by 3, x equal to 2, x equal to s, which gives us s cube minus 8 over 2 over 3. Okay, so v of s is equal to s cube minus 8 by 3. Since the volume of water after 1 hour is 19 by 3 meter cube, the height of the water level after 1 hour should be, we have to find that water level. If this volume, if the volume is equal to 19 by 3, s cube minus 8 by 3 has to be 19 by 19 by 3. So this gives us s is equal to 3. So after 1 hour, the height of the water is, height of the water in the pond is 3 meters. Okay, this is something that we will need a little bit later. Currently we have v of s equals s cube minus 8 by 3. Differentiating both sides with respect to the time gives us d by dt of v of s equal to 3s squared, or directly is a very simple derivative, ds dt. We want this ds by dt, the value of ds by dt, that is the rate of change of height with time, or as the question of at what rate is the water level rising, so that is just ds by dt. We want this. Now we have been given the value of d by dt of v of s, that is the rate of change of volume, or the rate at which water is being filled, that is 19 by 3 cubic meters per hour. So ds dt is equal to 19 by 3 over s squared. Now we want to find the value of ds dt when t is equal to 1 hour. This is 19 by 3 over, since after 1 hour the height of the water is 3 squared, and the answer is 19 by 27. 19 by 27. Sorry. Water level rising. So the water level height, this is meter per hour. And this is our final answer. So we are done with all the 8 questions of this paper. This was definitely one of the tougher papers. Unlike in 2020 when the paper was very easy, it was comparable to 2019. 2019 had a pretty tough paper too. This was one of the tougher papers, and as you will know, the cutoff for this paper was also very low. So don't worry if you can't solve all of the questions when you sit to solve this. This was a tough paper. Even I could solve just 4 questions in the exam hall. So be pretty satisfied if you're done with about 3 or 4 questions in 2 hours time. Okay, so that ends our discussion about this UGB paper of ISI entrance 2021. So yeah, bye.